we have a paper coming out on the mechanics of origami, and I thought I'd tell you a little bit about the general strategy that we have and how we're thinking about this, this field. The particular paper that we wrote in Science deals with the Mura-Ora fold. This is basically a series of parallelograms that, when folded into a sheet of paper, give that paper some mechanical properties that are determined by the fold patterns that we put in to the paper itself. The nice thing about this strategy for giving materials mechanical properties is that by changing the fold patterns, for example, I can give the paper a different effective stiffness. I can also introduce new novel mechanical properties. For example, if I take a banana and I just squish it in my hand, that banana is going to squirt out the other ends. But this particular pattern, if I expand it in one direction, expands in the other direction, and if I contract it, it contracts in the other direction. Okay, so it has what's known as a negative Poisson ratio. And that sort of speaks to what's so amazing about these materials. We can program in folding patterns that determine the mechanical properties and give us new properties like this negative Poisson ratio that we couldn't get with materials on their own. The paper that we wrote also highlights another feature, which is that you can program this Mura-Ori's stiffness. And the way I do that is by introducing pop-through defects. So I take one of these vertices and I pop it through. Okay, you can kind of see that on this side here. All right, the sheet is no longer quite as flat as it used to be. But the amazing thing about this is that whereas before, so if I don't have the pop-through defect, I could fold the sheet pretty easily. When I do have that pop-through defect, that sheet cannot fold any further. It becomes stiffer. And by arranging these pop-through defects on my sheet, I can effectively tune the mechanical properties. So this is a form of programmable matter, where we can not only fix one pattern and get one set of mechanical properties, but we can change that pattern on the fly. But origami is this sort of vast world of folding patterns, which give all sorts of interesting mechanical behaviors. I could imagine making a machine out of this sort of fold over here, where I have an actuator. Just by squeezing in on the inside over here, I'm getting this pattern to stretch out on the outside. And so this brings up the basic question of what is our global strategy for these origami materials? Just by designing their patterns, we can make anything from unique mechanical properties to switches. This is an example of a square twist, where if I pull, I can unfurl it, but if I just push it a little bit, you can see it snaps into place. And that's an example of a switching pattern, right? You pull, you don't get anything, but you pull hard enough, and eventually it opens. Okay? So these mechanical devices, we can now think of implementing them, but probably not on the paper scale. I and my colleagues would really like to think about implementing these on smaller and smaller scales. What happens if we could make these kinds of structures out of gel sheets that are only a micron thick? What happens if we start making these patterns out of graphene? Okay, so that's the thinnest sheet that you could ever possibly do origami on. And the idea here is that when you get to smaller length scales, it's often difficult to do the same things that we take for granted on large scales. So for example, if I was to build a robot on a macroscopic scale, I might take cloth from somewhere, maybe a steel chain, maybe a metal rod or some wood, and construct appendages. But on the nanoscale, getting this variety of materials is often prohibitive. It's often very difficult to do that. Our thought is, can we start, instead of trying to take different materials, can we start with the same material, something like graphene, and then by folding it or cutting it into different shapes, could we give it new mechanical properties based on the folded and cut patterns, and in that way make the different materials that we need for our nanoscale robot? That's the idea. I hope I've conveyed, just how much fun these patterns are, and the range of possibilities that we have for working with them.